During this last and final lecture, I'd like to focus on causality, and there's a lot of confusion about causality. And we're attempting to identify determinants and causal links to prevent and control morbidity, mortality, unintentional injuries, and disabilities. And what we're really trying to say is that A causes B. Because if we know what causes a particular um, disease or death or whatnot, we have the ability to prevent, protect, and control. So, but causality is its primary focus, as I mentioned, is right here. If A causes B, or that's what we hope, and we always hope it's simple, but it never quite as simple as uh, what we think it is. Now, there's two types of causal judgment. Overall, for an area, okay, um, we might take breast cancer, and we might have a determinant that causes breast cancer, and one study at a time. So I want to show you the one study at a time method because we're going to come up with studies that support a hypothesis, studies that do not support a hypothesis, and studies which are ambiguous and we don't know whether they support a hypothesis or not. So we're going to come up with three stacks of studies. Okay? Um, Now, it's very important, and a lot of people this is where the confusion starts. Statistical significance from one study alone does not prove or disprove a relationship, even if a particular event is 99% probable. Okay, for example, my mother was a very bright woman and was reading JAMA, and they were doing a study about wine and the effects of drinking 2 glasses of wine per evening. It had a beneficial effect, and it was statistically significant between the two groups in terms of, I think it had to do with coronary heart disease, and it reduced the risk. And I think it was a positive factor. It was below 1, so it was 0.78 or something of that nature. Now, she wanted to conclude that there was a causal relationship between wine drinking and reduction of risk. And I told her, I said, well, Mom, at your age, it probably wouldn't make too much difference what you did as long as you didn't overdo it. But one study alone does not indicate causality. It's the bulk of the studies, and here's the best way to say it. It's the preponderance of evidence in a given area is what proves the hypothesis. So, if, let's say, for example, um, if you um, if you had 8,000 studies out of 10,000 that showed a harmful effect, like we did with smoking, or 80% that showed a harmful effect, you would say that's a causal effect between cigarette smoking and some particular health problem because it's a preponderance of evidence in a given area is what proves the hypothesis. Now, let me back up. People say, well, how many studies do I need? And probably the best educated statement I could make is as many as you can get. But you're going to you notice that the preponderance, we had 8,000 versus 10,000, or 80% of them showed that smoking produced harmful effects. And of course, we knew this earlier than 1959. We just couldn't get any action taken because of the politics involved and the fact that the tobacco company companies had more money for lobbying than did health agencies. And this is still the same case. And it was important to the tobacco companies that this information not be shared because they didn't want a reduction in products. And I want to go on with this smoking idea. For example, changing the level on cigarette packages from may to is harmful to your health came based on the preponderance of evidence. And what we mean by that, we mean there were studies done by different investigators in different parts of the country with different study designs that arrived at the same conclusion that the rates for smoking exceeded the null hypothesis and generally were 2 or higher. Okay? Now, people say, well, you didn't have, if you had 10,000 studies, why didn't you have all 10,000 showing the same outcome? Well, roughly the 2,000 were done by the tobacco companies, and there seemed to be some bias in the way those studies were conducted. And I had the opportunity to listen to hearings on public television about smoking and whether smoking was harmful to your health or not. And I remember one study, one senator who spoke that was supported, got most of his campaign funds from R.J. Reynolds, and he was the one that was contending that smoking was not harmful to your health. So we often have evidence that gets suppressed, and evidence gets suppressed and is not used by those responsible for our laws and policies. And so it may take several years before it becomes evident that we should not be engaging in a certain behavior. And it doesn't, seemingly it shouldn't take as many years as it does, but it's a political factor supported by money or economics. Now, I want to go back to examining one study at a time and what it involves. I said there was 2 methods. You could do it overall for an area, and I just showed you overall for an area. Now what I'm doing is I'm showing you, I'm going to examine one study at a time. Okay? And here's how we go through it. 1, we test an epidemiological hypothesis with this one study. We look at this, we examine this one study. Let's say this study is done by you and 2 classmates, and it has an odds ratio, or it has a collection of information that indicates that smoking is harmful. Okay? And so next thing we would do is note whether an association or direct causal link, right? Association, we know those to be what kind of studies? Those are observational studies. This one is going to show the direct causal link would would be an experiment exists between a particular exposure and a disease versus those unexposed and without the disease. Okay, so this is what we have tested and found in examining one study. Okay, and epidemiological processes are used to aid in determining causation via clinical observations. As a practitioner, what do you observe? What do you note? Do you note that, these are the way we come up with new diseases, new treatment techniques, etc. So you see that with a few people that come to your office, that smoking seems to cause heart disease, or you see more people who smoke that have heart disease. And then we look at data analysis of experiments and observational studies. But we're just looking at this one study now, and it could be either an experiment or an observational study, and it seems to support this statement here under that's labeled number 2. Now, we could have multiple studies with different designs and investigators coming up with the same conclusion. Okay, but we're still got to examine one study at a time, and if we did have another study, we wouldn't have to have the same study design. It wouldn't have to be a case control study. It wouldn't have to be an experiment. We would have different study designs and different investigators in different parts of the country coming up with the same conclusions. So let me go back. I'm gonna take this one study that you and your classmate have done. Then in the process, I'm going to examine that study and come up with it, whether it supports the hypothesis that we have here. And if it does, it's detrimental to your health. If it's got a positive factor under 1, then it's in a pile different than those that are detrimental. And then we have a pile where we can't tell what's gone on, whether we have a 1 or a null hypothesis that's being supported. Okay, next, what we're going to do is we're going to look at bias. We're going to examine the quality of the data and the validity of studies, examining to see if bias accounts for the results or skews them. So if I were going, I'm still looking at this one study, and I'm looking for all of these different types of bias. In fact, when I review an article for a journal or a grant or whatnot, I look to see whether these types of bias are operating. If these types of biases are operating, it means that the study is problematic and probably the results are invalid. And so I would put that in that middle category because it's no good, or excuse me, I'd put it in the third one. My apologies. I put it in the middle one because it's not protective. It just, we can't tell what to make of it. Now, I'm not going to go through these, and these are all in Porta, the epidemiological dictionary. He defines every one of them, and you can go through and look at them yourself. But ascertainment bias means that it's a systematic failure to represent equally all classes of cases or persons supposed to be representative of the sample. So one example is patients coming from a specialized clinic. Well, that's not a representative sample. Or including all females and not males. That's not representative either. Now, white hat bias, and I think we run into this too often, this is when we attempt to find or report what society wants to hear. And in the social science, we call that response bias. And if you want to look at another one, recall bias is that you're going to recall something in a biased fashion that fits your values or some norm that is operating. Okay, so you can go through and learn more about these types of bias. I'm still examining one study at a time, so this one now is in the middle category because it's got one or more types of bias. Okay? Next, I want to talk to you about a confounding variable. Most people don't understand them. And I want to show you a picture of it because it'll be easier to understand when I do that. And all confounding means is two variables mixed together or two ingredients mixed together. So you don't know what's responsible for the effect, okay, or the outcome. Confounding might also indicate a mediating or a moderating variable, and I'll talk to you about that in just a minute. I'll show it to you. A mediating variable is statistically associated with the independent and the dependent variables. A moderation variable is a third variable exhibiting statistical interaction by virtue of its being an antecedent or an intermediate in the causal process. I know you don't understand this. Don't worry about it. I'll clear it up in here in a second. Unless it's possible to adjust for confounding variables, usually done or confirmed statistically, their effect cannot be distinguished from the factors being studied that are really in the causal link or in the causal process. Bias can occur when adjustment is made for any factor that is caused in part by the exposure and is also correlated with the outcome. Okay, so we're going to talk about, the most important term I want you to get out of all this is confounding. A confounding means a variable that two things are mixed together and you don't know what causes the outcome. All right, now let me show you a picture of it, and I think I can clear it up for you. In the beginning, this slide points to the fact that coffee drinking may be confounded by smoking. Both coffee drinking and smoking may be associated with pancreatic cancer. It might also explain a mediating and moderating variable. Well, when we first started out a few years ago, we thought that coffee drinking was responsible by itself for pancreatic cancer. Then we found out that coffee drinking and smoking together were responsible for pancreatic cancer. It wasn't until later that we found out the degree to which coffee drinking versus smoking was responsible for pancreatic cancer. But we jumped to conclusions originally by just making this direct link and connection between the two. Okay? Now I want to talk to you about a mediating variable. Smoking is statistically correlated with coffee drinking and pancreatic cancer, and the areas would go both ways between the dependent variable. This is the dependent variable. This is the outcome of interest, pancreatic cancer, and the independent variable, coffee drinking. Okay? So in this case, they would go both ways. Okay? The moderating variable. Smoking is statistically associated with coffee drinking, and the two in concert influence pancreatic cancer. So smoking is connected to coffee drinking, and the two have an impact on pancreatic cancer. That's a moderating variable. Okay, so hopefully if you want to play that back, you can get it, and it should be clear to you what the difference is between a mediating and moderating variable. But the most important thing is I'm trying to point out is confounding and under-confounding is the type of confounding which is mediating or moderating variables. Okay. Error. Two main types of error, and I think you'll find these interesting. They're random error and systematic error. Okay, random error. It's an error due to chance. There's no association with any other known variables. For example, a random error is illness affecting your GRE score. Okay, and we found out that, for example, I gave you that an illness could be influenza. You don't have influenza every time you take a GRE score. or you don't have a migraine headache every time you take a GRE score. So those illnesses are random errors. They don't occur repeatedly. Now let me talk about a systematic error. And it says the portion of variation in a measurement that originates from a recognizable source. And these are all the types of bias shown previously, such as white hat bias, finding what the population wants to hear, or a poor exam question. These are going to be systematic. They're going to happen every time. A poor exam question is generally going to produce a poor result. And a white hat bias is a conclusion drawn that's not based on fact. It's based on something other than fact. It's based on what somebody wants to hear. Those are systematic errors. There's nothing random about that. You getting sick is a random factor. Now, there's another type of error that has to do with a type 3 error. And a type 3 error is developing and implementing a poor quality intervention that is irrelevant or simply has no chance of producing an effect. And we think about, I mentioned type 1 errors, I mentioned type 2 errors, and I've also mentioned a type 3 error before. So this is a systematic error. If you produce something that's lousy in the way of an intervention, it often doesn't produce the desired result. And this will occur patient after patient after patient after patient. So these are errors. And these distract us from obtaining a valid and reliable finding. And the only way I could manage a random error is by replication. So if you had a migraine headache the first time you took the GRE, and what we do is give you the GRE again when you didn't have a migraine headache and see what the difference in scores were. Okay. Now, I want to put this into effect and into another type of diagram. If we were going through and we're still looking at one study after another, everything I've said is pertaining to one study, okay? One study, okay? And so first off, we say, are the findings due to chance? If yes, we're going to put it in that middle pile. Are X and Y due to chance, or is the association real? If the association appears to real, we say, no, it's not due to chance. Then we go down and examine bias. If it's due to bias, then we're going to toss that study out. Deviation of results from the truth as a result of flaws in the study design, data collection, analyses, or interpretation of results. And then we ask, is it due to confounding? If it's due to confounding a variable that can cause or prevent the outcome of interest, the variable is associated with the factor under investigation but must be controlled. Okay, and we talked about age, sex, race, smoking status, body mass index, and healthcare expenditures. So if any of these operate, this study is not in support of the hypothesis that the independent and dependent variable are associated or A causes B. Okay, so it's not, we can't have confidence in this one study supporting that A causes B. All right? Now, I want to show you other ways to evaluate studies. Excuse me. These are criteria from Sir Bradford Hill. And stop. Okay, I'd like to talk about formal criteria for examining one study at a time, and these come from Sir Bradford Hill, and they are well known and often used in epidemiology. And I want to let you know that you can read about these in just a few pages in Epidemiology Kept Simple. That's one of your texts for the class. It's on page 294 to 302. That's 294 to 302. Now we have statistical methods. I want to be sure I mention this. So we have statistical methods of evaluating studies, and they're measured in standard deviation units, and it's called a meta-analysis. And in an advanced statistics class, you would learn about a meta-analysis. That's a statistical quantitative method. We're going to use a qualitative method. In epidemiology, we still use qualitative methods to talk about causality or whether there's a cause and effect. I also want to mention that we're using this for each and every study because I'm still dealing with looking at one study at a time. Now, I want to go through and give you an overview of each of these before I get into showing you figures or graphics of what some of these mean. Now, I don't have graphics for everyone because they're not appropriate. But what we mean by strength of association is that we're going to look at relative risk, odds ratios, and confidence intervals. And all a confidence interval means is the percentage of the time that you're going to get the same result if you did the study over and over and over again. So if you have a confidence interval of 95%, it means that if you did the study 100 times, 95 times, you would get the same result. Okay, I want to talk about a dose-response relationship. We learn a lot about this from pharmacy. You know, what level of drug do you need in your system to have a therapeutic effect? But this says a dose of exposure increases as the risk of disease increases. So this is the negative side of the positive that I mentioned in pharmacy. So if I get greater exposure to asbestos, does the risk of disease increase? That would be support for our hypotheses of asbestos being detrimental to one's health. Now, temporal relationship. Does exposure precede the disease? And I'll show you that. And specificity, and this is a different meaning of specificity than what you learned with screening test. Is exposure specific to the disease? And consistency of association. Is there consistency in the findings reported in different studies using different study designs conducted by different investigators across the country? And I'll substitute words in here so that maybe they'll connect with your past and your prior training, so it'll be easier for you to remember. Now, we have there's 9 of these, and these are the last of them, and I'll go through them in a systematic way. Is there a plausible or a credible biological or physiological mechanism to explain the development of the disease or increased risk for the disease? So this comes from biology or physiology. Is another way to say it, and this is not quite right, but it might help some of you. Is there a theory that supports this? Okay. but does it make sense if I was going to explain it from a biological perspective or a physiologic perspective? Now, coherence. Does it agree with known facts or existing knowledge? Now, this is interesting because, the theory that was reigning during Snow's lifetime in 1854 was miasmic theory, or bad air. Well, his findings didn't agree with that theory at all. Didn't make his findings wrong. Made the theory suspect. Okay, experimentation to rule out alternative explanations. To what extent has the possibility of alternative explanations been considered and excluded? For example, here we go again, back to what I was talking about: chance, bias, confounding. This is accomplished by experimental, observational, laboratory studies, and animal models in support of causal relationships. Yeah, stop it. Gotta stop it. Okay, I'd like to continue with Bradford Hill's criteria and talk about the biological plausibility. All this means is, does the data, the outcome, agree with biological or physiological mechanisms? Could a biologist explain how this disease might occur, or a physiologist explain the mechanisms of the development of the disease? Now, coherence is different. It has to do with known facts or existing knowledge. And I wanted to take you back to Snow and cholera in 1854. Remember, the primary theory there was miasmic theory, or bad air. And of course, that had nothing to do with the disease, and that theory was bogus. And even after Koch talked about cholera and discovered cholera, many scientists continued to believe in miasmic theory. Now, I'd like to tell you that that was just the case then, but we have new discoveries all the time that don't seem to fit with a particular paradigm or knowledge, or fit with a biological or physiological mechanism. So that doesn't mean the results are wrong. It may be that our background and things that exist currently haven't caught up with what's really happening in our society, or in a particular medical area or some other professional area. Now, we covered this before. We're trying to rule out alternative explanations, and to what extent has the possibility of alternative explanations been adequately considered and excluded? And remember, we talked about chance and bias and confounding. Are these operating? And this is accomplished by experimental, observational, laboratory studies and animal models in support of a causal relationship. Now, analogy. Does an analogy about something offer insight in the connection among unknown variables and help to support a causal relationship? So those are generally the methods in epidemiology that we use to evaluate a particular study. And I'm going to go through these one at a time, and I want to talk about them and show you figures if they're applicable. Okay. Now, this is to put it into context. By examining a single study at a time according to Bradford Hill's criteria, the reviewer ultimately comes up with 3 stacks of studies. And I mentioned this before. Studies that support causality, studies that do not support causality, and poorly designed studies in which results are inconclusive. If the stack is higher for causality than non-causality studies, the evidence favors causality, depending on the difference in the number of studies for or against. So again, if you get a higher stack that support causality than those that do not, then you rule in favor of causality. Next, we talked about the strength of association. And all this means is it's either relative risk or an odds ratio. And we say the stronger the association between the cause and effect relationship, the greater the probability a causal relationship exists. And I show you the criteria below. So if you have a study that is under 2, you get an odds ratio or relative risk under 2. That's not very supportive for a causal relationship. If you're getting a relative risk or odds ratios between 6 and 10, you got a lot more confidence that there's a causal impact, because those are very high values. Now, the next one I want to talk to you about. So, now, before I go on, I wanted to mention that if you get a if you get a relative risk or odds ratio of 2, usually you can think about that in probability terms. So if you were going to get a p-value, probability value for a study, usually with a 2, it'd be a probability of about 10 zeros and then a number or 1. So it would, just figure a p 0.00000001, and that would be what would be equivalent to a 2. So you can see that a 6 to a 10 is a very significant result from a point of examining it in relationship to probability. Consistency of association. Okay. Now, really what I'm going to talk about here is reliability. If I've got, let me just go through this with you because I know most of these slides by heart and I take shortcuts, and that doesn't do you any good, and it may confuse you. So when we talk about consistency, what we're looking for is a finding that happens over and over and over again. And a finding that happens over and over and over again is called reliability. So consistency equals reliability. But we mean in this case also that we have a different research team, different settings, and different circumstances, and in every case we find the same kind of conclusions supporting causality. Now, the larger the percentage of studies that demonstrate a relationship, the stronger the evidence. Let me give you an example. For example, we have 31 studies that favor causality out of 35, or 89% of the studies found an association. There have been about 35 studies conducted since 1962, and higher titers of measles antibodies were found in multiple sclerosis patients in all but 4 of them. So this criterion would lend support to a causal hypothesis involving exposure to measles. Okay? Now, 89 demonstrated consistency, only 11 did not. Okay? So again, what we're finding is it's consistent. So this would lend, anytime we have consistency, this lends support to the causal hypothesis, and in this case, um, measles, being exposed to the measles resulted in multiple sclerosis. Okay, specificity of association. I'm going to show you, this term has a couple of meanings. I'm going to show you one meaning first. And ideally, what we would expect with any disease is you'd have one determinant and one outcome. But that doesn't always happen that way. Now notice, for example, that obesity increases the risk of stroke, diabetes, and coronary heart disease, and the three together impact heart attack. However, all these conditions may arise from other causes. So we have to be careful, but what we hope in explaining any disease that it has one cause. That makes it easier to treat. And I want to show you another example of this because, people say, well, why don't we make progress with a given area? And why don't we just have a univariate explanation? We have one cause, we have one outcome. Let me show you the simplified web of causation applied to cardiovascular disease. Look at all the various factors that have influence on cardiovascular disease. So, when we have multiple risk factors, this is what we talk about, multiple risk factors, it makes it much more difficult to explain a causal relationship where one determinant explains one outcome, because we have a whole lot of factors having an impact on cardiovascular disease. So all of these factors seemingly have that impact. We're a little less uncertain about stress and whether people are obese because of stress. Recent research shows that that's the case. Stress does plays a role in the erosion in the erosion of the brain. We also note that smoking does affect blood clotting. So anyway, the point here is we have multivariate determinants that influence cardiovascular disease. Now, here's the second definition of obesity. Now, notice this. This is cancer mortality ratios, and you know immediately rates, and proportions among men with a history of cigarette smoking compared with men who never smoked. Okay? So, when we talk about specificity in this particular means, we mean that the smoking, we're hypothesizing that smoke ought to have higher ratios and detrimental effects among those parts of the body that smoke directly comes in contact with, right? Well, it's going to come in contact with the lungs. It's going to come in contact with the pharynx. It's going to come in contact with the larynx. It's going to come in contact with the esophagus. But it doesn't come in contact, direct contact, with a lot of these other sites in the body. So we ask ourselves, in terms of specificity, are the ratios higher where it comes in contact? And we look at the lung and look at the odds ratio or the relative risk that we're getting. It's very high. Then we come with pharynx, and then it's high here, but it's not high here in the different age groups. And then we notice that the larynx, it's high. And then we notice with the esophagus, it drops off. It's high here, but it drops off. Now, we notice that some of these are high, but they're not nearly as high as what we see up there. So it supports the hypothesis of specificity. Now, what it doesn't support is the hypothesis of consistency, because we would anticipate that the odds ratio or relative risk for total cancer for both age groups would be the same or higher, right? And we notice that this drops off. And we notice that for the esophagus, it drops off. Well, why does that happen? Why aren't we finding a consistent result? Well, the answer is that we think it's due to the fact that people who smoke die at 65. And so these ratios are very much affected. These odds ratios or relative risk are very much affected because this group is dying. And that's why their values are less in the 65 to 79 year age group. But that's specificity, and this is the specificity part. This is the consistency part. Okay, so specificity has to do with parts of the body that directly absorb smoke. Okay, and it looks like that hypothesis is upheld. Okay, dose-response relationship. Let's talk about asbestos for a moment. The reason we got Bering Hall is because we used to have asbestos in the School of Education that was where Bering Hall is now. And people in the basement of the old School of Education, the longer they were there, the more likely they were to get asbestosis. So what we saw was a dose-response relationship. So you can see this is time, and the longer the time spent in the building, the more likely the response was to occur and the greater the response. So the longer people are employed, the higher the exposure, thus the greater the risk and likelihood of fibrosis. Okay, so this shows you a dose-response relationship, or also called a biological gradient. Either term is correct. So dose-response relationship or biological gradient. Next, this is another one about maybe it's asbestosis in this case instead of fibrosis, but you're getting the idea. This is incidence versus years of employment. Now notice, if more of the exposure leads to more of the disease, this is a dose-response relationship or biological gradient. The case for a dose-response relationship and causality is strengthened. Newhouse cited data gathered by Meriwether and Prince that showed the relationship between the duration of employment in the asbestos industry and the incidence of fibrosis. Okay? So I had a relative that was an engineer, and there was engineer for the railroad, and there was asbestos. The engines were asbestos lined, and he would feed that engine with coal. And what occurred is that his dutiful wife would shake out his bib overhauls and then wash them. And when she shook them out, um, asbestos was released into the air before she threw the clothing into the washer. They both died early from asbestos. Biological plausibility. If it makes sense from the perspective of biology and physiology, there is a greater plausibility of a causal relationship. Okay? Um, it may also mean, though, that theory or research may not have caught up with science, hence does not make the outcome untrue. And that's what we said earlier about Snow and Koch. So I just caution you about using this particular criterion to conclude causation. Okay. Now, I think this is sort of important. Until recently, no known biological or physiological mechanism existed to explain how psychological stress could result in greater susceptibility to infectious disease and cancer. Well, we're finding that stress often leads to depression, and as I said, we have found physical erosion of the brain from people who have been depressed for a long period of time. Now, only within the past several years has it been shown that stress may produce immune suppression by affecting immune cell functioning, and as was the case with the criterion of specificity, plausibility strengthens the hypothesis, but lack of plausibility does not weaken it. So, biological plausibility is important, but yet again, science may not have caught up with where we are in a particular field, and we don't have the mechanisms to explain the problem, even though the problem does exist. Okay, coherence, knowledge or factual basis. When discussing plausibility, we note the absence of a plausible theoretical or scientific explanation does not necessarily indicate the phenomena found is untrue. Rather, it may reflect our ignorance. The data may be ahead of its time. Okay, on the other hand, the postulated causal relationship should not conflict, and there's a real statement, should not conflict with existing knowledge or facts about the disease or the data. Okay, coherence. Coherence has to do with whether the phenomenon makes logical sense or conflicts with knowledge. Although coherence does not have to correspond to current theories or scientific outcome, it should make empirical sense. Next, do the findings about the relationship in exposure and disease agree with known facts or existing knowledge? It would be nice. And this is the one I think that often occurs, and this quote has always meant a lot to me. And when I think back about AIDS, when it first came on the horizon, we had hundreds of hypotheses about it. And I think this quote is wonderful. It says a number of different hypotheses used to explain a given biological phenomena is inversely proportional to the availability of knowledge. So the less we know, the greater the number of hypotheses about what is responsible for the cause and effect relationship. experimental instances. In some cases, there may be experimental incidents that suggest a causal relationship. And this is the general model that we use to prove something or to verify something. We start with animal models, then we do experiments in laboratory settings, and then we do controlled randomized trials. And you will hear a lot about the value, but NIH is shifting its opinion about controlled randomized trials, are also known as double-blind studies, experiments in nature, observational studies and experimental studies, and last, prospective studies with preventive interventions that demonstrate that A precedes B. So if we have all of these going in the same direction, we have more confidence that there's a causal relationship. Analogy. This is the weakest form of evidence. An analogy is very similar to biological plausibility. For this reason, many authors do not properly distinguish between the two and drop this last category from the list of criteria for causality. The causal relationship is explained via an analogy, not plausibility or coherence. And analogy is anything well known that is used to explain something unknown. And here's an example. You could use a thermostat, and this may not be a good example, but it's one that's cited. When the heat is turned up, pressure in, for example, you have a lot of assignments due at one time, stress occurs. So you can think of turning the heat up on the thermostat. When the thermostat is turned down, you have fewer assignments, stress is less. So now, does that thermostat explain the way stress operates and help to talk about and explain causality? That's the question. And this is why it's often dropped. Now, 3 cognitive methods of causality: biological plausibility, coherence, and analogy. And from philosophy came methods to develop proofs, and hence the development of a doctorate of philosophy degree. I always tell people that before we had a computer, we had to have a means to determine or ascertain whether something was causal. And we did it by thinking processes, and we used cognitive methods, and these are all cognitive methods of deciding on causality. And we rely on those to help make the judgment of causality. Now, note, you need not meet all criteria to determine causality, but the more criteria, the better. For example, for causality, notice this: you do not have to satisfy the condition of dose-response relationships, biological plausibility, or coherence. And I sort of like to summarize at this point and say different books and different authors present many different criteria. However, the factors are often very similar, and I can vouch for that. I've looked at all kinds of books on epidemiology over the 30 years of my career. And nothing in life is certain except for taxes and death, and maybe you can get out of taxes, I don't know. But the information may be temporarily useful to make important decisions and add to our knowledge base to move science and knowledge forward. Okay? And as Hill said himself, all scientific work is incomplete, whether it be observational or experimental. All scientific work is liable to be upset or modified by advancing knowledge. That does not confer upon us a freedom to ignore knowledge we already have or to postpone the action that it appears to demand at a given time. Well, I hope you enjoyed this class. You probably feel like you've been fed out of a fire hose. I hope it hasn't been too overwhelming, but I can say with certainty that I have confidence that you will use this information throughout your career and it will be valuable to you. We have selected that which we know is important to your future, what and that most of you will be supervisors and supervising others. And you will find that having um, a vocabulary that is well grounded will help you in explaining science to others. So, with my deepest wishes for a successful future, I will terminate my lecture, and this is my final closing. Thank you very much for attending the class.